Okay, Assalamualaikum and a good afternoon. So, welcome back. So, we're off to another half semester to finish this course. So, probably we should start right now. But before that, I presume that you have seen all your test one results. I have to do something with respect to those who gets marks less than 8, which is actually 40%, okay, which is the passing mark. So please contact me individually for those who are for those who are getting less than 8 marks for the test one. Okay, so we need to probably meet about 10 minutes, okay, and discuss what you have done inside your first test. Okay, so let's move to the lectures. So we have not finished lecture 8, so I believe we have gone through all this until somewhere probably here. Okay, so here essentially one looks at, again, the idea is to be able to do analysis of geometry, which involves lines and planes, to be able to do some calculations with that using using vectors as tools. So here is an example I did mention last time. You are looking at a particular point P from a line, and we would like to find the distance from that point to the line. So essentially this is the point. Okay. This is, if you look at that, that should be equals to the line PQ sine theta. So PR equals to, so actually it's down there. Okay, so better not repeat that. So the length of PR over here is essentially PQ sine theta, and we have seen what kind of operation that gives you sine theta in this particular case is your cross product. Okay, so A cross B, for example, is equals to length of A times the length of B sine theta. So one can actually try to use that, and in this particular case, one would like to use this vector Q, okay, this vector PQ, and this vector QR. So we need to find the vector QR in some way. Okay, so here usually we choose Q. Q is chosen, and then we need to find R in some way, but that would require us to know what this particular vector is. Okay, so this vector sometimes is given, otherwise you have to find out. Okay, so in this particular case it seems to be given. Okay, and what we need is to find a unit vector, because you want to get rid one of the lengths of these vectors here. So you want the unit vector, and then you are just left with the PQ here, and then with the sine theta. Okay, so that is what we need. So let's look at a particular example here. Is this example 4, to find the distance of P from the line joining P1, which is at the origin, and P2 at -1, 0, 2. So in this particular case, the line here is P1, P2. Okay, so this is P1, this is P2, for example. Then you have that same picture. Just now, we have P somewhere here, so we need to find the vector over here. P1, P2, you can actually find the vector here by just taking the difference. Okay, remember this, you can think of that, for example, and that is the difference between the two vectors over here. Okay, the previous example, this one, right? Okay, so this is the difference of the two vectors. Okay, so one takes the difference of these coordinates, okay, which are position vectors for each of these points, and you'll find that that is equals to minus I plus 2k. Okay, and in order to find the unit vector along this direction, okay, so you need to find the norm of that vector, which is given by minus 1 squared plus 2 squared. Take the square root, and that gives you square root of phi, and essentially your u here is now taking this vector divided by the norm here will give you the necessary unit vector. Okay, and then what else to do is to find the vector PQ just now. Okay. So the vector PQ is just you are given the point P. Okay, so you need just to find another point on the line. Okay, so here's the point on the line been given by just taking simply P1. Okay, and you take the difference between the two, you get the vector PQ, and essentially that gives you minus I minus 2j plus k. Okay, so the next step is to use that formula. So this is PQ now, and this is U, and U is already unit vector. The square root phi has been taken, one of square root phi is taken outside. And then you just simply take the cross product. So here you can just simply use consecutive what you call cross product of each term. So minus I cross minus I gives 0, minus I cross 2k gives you, what would that give you? That would be k cross I, that would be j, and then minus 2j times minus I, that's j cross I, that gives you minus 2k. Okay, and then finally you have 2j times 2k, which gives you I think that should gives you 4i, but you have a minus sign there. Okay, so that gives you that vector from the cross product. So essentially now one needs to take the magnitude of that. So the magnitude of that is just this thing, minus 4 squared plus 1 squared plus minus 2 squared, and then essentially you take the square root of that, and that gives you the answer. So always to have good visualization, and then what's the input data. Okay, in this case you are given the 2 points on the line, so that makes it easier, and then you also are given the point beyond the line, and that gives you the point P. Okay, so always be clear of what is the given data, and then how to actually draw those vectors that gives you the formula that you need. Okay, now here's another interesting problem. So unlike the one before, you have a point, and then you have a line, and then basically you want to find the perpendicular distance. now you have two lines. So here's two lines, and they are not necessarily what you call, they are not on the same plane, and also they are not in the same direction. So in other words, what one needs in this particular case, here is the line here on each of their planes. Okay, so what one needs is the closest distance between the two lines would be the one which is normal to each of these lines. Okay, so again, in order for you to find a particular distance over here, so let me just check because I can't remember what's the thing they asked. Right, okay, it's still the same thing, the perpendicular distance. So the perpendicular distance over here will depend on this particular vector here, and PQ are points on the line. Okay. And then one needs to find out what would be that distance between these two lines. So again, over here is good to have some visual aid here. So one expect this normal going to be parallel over here, and then you find that okay, there will be some angle over here. I think this will be the angle, so that will be the angle theta, and then essentially we want that distance which is given by PQ dot n. So essentially that gives you the cos theta there, and then that would be the job to do. Okay, the only thing is, how do you get n? So n is taken from the two vectors that give you the line. Okay, so here's the line A, here's the line B. So in order for n to be perpendicular to both, then it needs to take the cross product between the vector A and the vector B. Okay, so that is what happens over here. So you take A cross B to give you a perpendicular vector to both lines, and then you take essentially the norm of that vector, okay, in order for you to get a unit vector. So okay, so let's look at an example so that one knows how to use it. So here's the question is to find the distance between these two lines. So this is the equation of the line, a parametric equation here. So here's the parameter, here's another parameter here for the other line. Okay, so again, here you can think of the basic equation is R naught plus A times T. Your A here gives the direction of the line, and here is a given point on the line. Okay, so so one can actually choose over here, for example, a given point on this line would be x equals to 1, y equals to minus 2, and then there's no component of k in this part, so you give you just take the z component to be 0, so that will give you the point P, and then the equation, the direction of the line is in this direction of this vector A, and similarly for that line for this example here, so this will give you this part will give you the given point. So that gives you 0 minus, sorry, 0, 2 minus 1. Okay. And then your direction of the line is given by j minus I. Okay. So just like before, what we need is the normal distance. Okay, so you need the normal to both lines. So you take A cross B, where A is that and B is that, and then you do the cross product, and that should be easy enough because there are only two terms on these two vectors. So you get I plus j plus k, and then take the norm of that, divide it by the norm, and that gives you the unit normal to that two lines. Okay. So the vector between the 2 points P and Q, again P and Q is taken from there. So you take, so remember that the idea is to find, you are more or less given the P and Q, so you can actually find this particular vector here. So that would actually give you this vector. And then that vector dot product with the normal will give you the distance between the two lines. Okay, so I will not go through all this numerical calculation because that's easy enough for you to do. There are two more work examples in the book, which is done very briefly. I advise you to look at it, okay, as an exercise at home. Now, it's crucial for you to have some understanding of how to solve this kind of geometric problems using vectors because they are really convenient for you to do. Otherwise, you have to work it in terms of magnitudes and angles, which are going to be more troublesome rather than using these vectors. Okay, so let's. I think I want to finish. That's already finished. So now we go to the next lecture, which is, I believe, the second last of the section of the chapter. I'm not quite sure what chapter is that. It's chapter can't remember what chapter this is. I think it's chapter 3, right? Chapter 3 on linear algebra. So this is section 12. So sorry, the one we are doing now is section 11. Okay. We are doing the diagonalization first, and then we look at some examples probably for the next lecture. Okay. So section 11 is the thing that we are doing now. Yeah. Okay. So again, this will build up on a few things that we have actually learned before. So let me just go through the notes. The notes are almost a direct taken out from Boa's book. I didn't have time to actually modify it according to my thoughts. Okay, so this is probably just a reproduction from Boas. Okay, so what we want to do in this particular case is to have the idea of eigenvectors for matrices and eigenvalues for matrices. And you probably have learned this before. Essentially, one looks for matrix M. Okay, one look for matrix M, and then you find a particular vector here, and then the eigen equation is given by that. So this is an eigen equation of M. So one needs to solve this. So this is given matrix, and one simultaneously solve for R and solve for lambda. So R is called the Eigen, so this is Eigen equation here. And so this is what we call eigenvector, and this is called eigenvalue. Now we would like to do this a little bit more geometric because one can do this just like an algebraic problem, but it's much better to be able to have some geometric understanding of this particular eigenvalue equation. Okay, so what we do is to think of your M as an operation on the vector R. Okay, so one can think of this like doing a kind of transformation there. So normally this capital R and small r here will not be the same. So basically there's a kind of transformation there. But what one needs is the Eigen equation would be something that reproduce this in the direction of R. Okay, so that gives you that. So this reproduce Eigen equation. Which is equivalent to this. Okay. Just checking my phone in case I get disconnected. Okay, so what one do is to begin with some example first. So here's a kind of transformation here. So here's your matrix M. Here's your vector small r being transformed by this matrix M to capital R. Okay. So one simply multiply this to give you an equation here. For example, this matrix times that. Okay, and then that will have to be equal to some lambda times the vector r small r itself. Okay, and then you'll be able to get the Eigen equation over here. And if you try to multiply out those matrices here, you'll get two sets of equations relating x and y in these two equations over here. Okay. Now, one can do something. Well, okay. One of the things that one can do is now to be able to write this as follows. So here, this part of the equation can be written as lambda I x y. So this will be equals to lambda 0, 0, lambda xy. It's the same kind of thing. Okay, so and then you'll be able to write the equation in this matrix equation. Okay, so this is m minus lambda I. Okay, and over here now, if this has an inverse, this matrix over here. So what one does would then, okay, if there's an inverse for that, so I can multiply m minus lambda I inverse times m minus lambda I, and then your small vector r equals to the 0 vector. Okay. Now, if this exists, then the solution will be just simply r equals 0. If m minus lambda I is invertible. So that would not solve your eigenvalue equation, so we need something different. That means we need m minus lambda I to be non-invertible. Okay. So what's the condition of a matrix not to be invertible? Well, to have an invertible matrix, let's say matrix A here, if this is invertible, then a necessary thing that one must have is that your determinant A is not going to be equal to 0, because your A inverse will be related to your 1 over determinant A. Okay. So in other words, one needs your determinant A to be 0 if you want it to be non-invertible. Okay. So in this particular case, you need this to be non-invertible, so that means determinant of lambda m minus lambda I to be equal to 0. And in that case, you will be able to get, in the case of a 2 by 2 matrix, you'll get a quadratic equation in lambda. So once solve this quadratic equation, solve for lambda, and then substitute back that lambda into the equation over here, and you should be able to get your eigenvectors. So this is, let me ask you guys, oops, what am I doing? Let me ask you guys, have you done this eigen equation for 2 by 2 matrix? Yes or no? Because I'm assuming that you have done it. Nobody wants to answer? Okay, if you can voice it out, it's much better, because I cannot see you. I cannot see the chat while I'm presenting. Okay, the 2 by 2 matrix, have you solved for eigen values and eigenvectors? I'm just checking now, because I'm not sure whether you have done it. I think you should have done it, but no, just checking at the moment. Have you done a 2 by 2 matrix, finding eigenvalues and eigenequation? Okay, that's great. That's all I need to know. Okay, because now what we're doing is just giving you some extra understanding of this eigenvalue equation. Okay, good. So that means I do not need to go into the details of the of this particular example, for example. Okay, let me just give you some names so that you'll be able to know what they are when people mention it. This whole equation is called the characteristic equation of matrix M, and the determinant is called the secular determinant, or sometimes the whole thing is called secular equation. So one can go on to find the eigenvalues in the normal way, and then you'll find that, okay, your lambdas are going to be 1 or 6 over here, and then once you have done that, you're going to substitute back into the equation, and then solve for R. So I'm not going to do that. Okay, probably it's down here anyway. Okay, so here is the now, okay, the essential thing that we want to do today is essentially this process, not so much of the eigenvalue equation. Okay, this diagonalization process. Okay, so we're really into that. Okay, you have done eigenvectors before, so now we want to use these eigenvectors to actually form what we call diagonalization process. I believe that one would be probably a slightly more advanced thing. Probably you have learned it as well, but usually this is slightly more advanced than just finding eigenvalues and eigenvectors. So let's do that. Okay, once substitute back this eigenvalue into the equation, then you get this 2 equation over here for each lambda. So you get 2 equation let me just check. Yeah, okay. The two equations over here is substituting lambda 1, lambda equals to 1 here, and then simplify it. Okay, just worry. Okay, simplify it, and essentially you get a particular relationship between y and x, and that gives you a line. Okay, so this is the line y equals to 2x for lambda equals to 1, and then you do the same thing for lambda equals to 6. Okay, you have the two eigenvalues just now, and then you simplify it, and then you get another line which is y equals to minus half x. Now for each of these, one could simply relabel these equations by selecting a particular x, say, and y for each of those lines. Okay, so here for lambda equals to 1, I use x1 and y1, and for the second line for lambda equals to 6, I use x2 and y2, and you can see that over here this is coming from y equals to, what was that earlier? I forgot now. Y equals to 2x. Okay, so you can see over here y equals to 2x, and the other one is y equals to minus half x. I'm not sure why this is not a minus sign. Let me check. Lambda equals to 6. There should be a minus sign. Okay, I better check that again later on. So now you have this expression for the eigen equations and eigenvectors over here. One could rewrite them. Let me just go back here. One could rewrite them as this set of equation equals to this set of equation. Okay, and one just need to multiply out these matrices and also these matrices to check that you get back your eigenequations. Okay, this one is probably familiar, but here instead of having just one R, okay, I have two of them here. So it's a 2 by 2 times 2 by 2, so you get essentially a 2 by 2 matrix. But now here is a different way of writing it. This is coming from the right hand side. So remember the matrix is this. Okay. So here, what do you do here? Because this is like a scalar here, I can do that. So essentially, now this R, I'm not just consider a single R here, I'm consider R1 and R2 here. So R1 and R2 here, so I get a 2 by 2 matrix there, and also a 2 by 2 matrix over here with this lambda given by this matrix 1 0 0 6, because this is the first lambda 1 and this is second lambda 2. Okay, so we write in this particular way to see this relationship between the two eigenequations. Now what one does is, the next thing is to normalize the eigenvectors that you have actually solved over here. because you know the relationship between x and y. So you solve for that. So in this case, it's x1 to x1. Okay. So in order for this to be normalized, so think of this as a vector now. So you normalize that. So that means I need this equation out. So in other words, once you have this equation, I'll be able to solve for what x1 is. Okay. So in this case, I will take x1 to be 1 on square root phi, and in the other case, okay, now there's the minus sign back here. That's good. So that means that what I mentioned just now, there should be a minus sign there. So again, you normalize that, and then you have x2 to be equal to that. Okay. Now put this what you have solved into this equation before. Okay, the equation, here's your mr1 r2 here. So I do not know how to write this, but you can think of this as r1 r2 here. Okay. And then this is again r1 r2. So put it back into the matrix. So essentially you have this m, the original m here, and we call this as C. Okay, these are the two x1, x2, and what was it? Y1, y2, x1, y1, x2, y2. Okay, so here you have your C here, and then here's the matrix using the eigenvalues, and we call this as the D. So D essentially representing what we call the diagonal matrix. Now written in this way, then you'll see that, okay, remember that this is coming from the eigenvectors. These are eigenvectors, these are eigenvectors. Okay, so all you need to be able to do is to find eigenvectors and form a matrix of them. Okay, and then I'll be able to write this, and then I can rearrange that so that if I'm pre-multiply this with the C inverse, I will get the following. And that is essentially what we have here. So in other words, we are converting this matrix M, which was given to us, into this matrix D. And this is this transformation, so to speak, is called the diagonalization. And this part is what we call a similarity transformation. Similarity transformation is something like, okay, if you have matrix M and then you multiply, say, matrix A inverse A, this will give you a similarity transformation. Of course, there will be conditions on that, because you need, for example, the A inverse to be definable. Okay. Now, how can we understand this process to start with? Well, really, if you look at the kind of vectors that we have here, here is something which is less than 1, something less than 1, the magnitude of them less than 1. Same thing here, it's the same matrix, by the way. So what one can do is to think of your C as a rotation matrix. Okay, remember what rotation matrix looks like? It's cos theta is less than 1. The magnitude of sine minus sine theta is also less than 1. And then there's sine theta and cos theta. And you can see that it has that structure. This is cos theta here, this is cos theta here, and this is sine theta, this is minus sine theta. Okay, so That's nice. Okay, now one can think of this just like a rotation of, say, a vector. Okay, so you rotate the vector, say, the vector r over here, okay, into a new vector, vector r dash, which is given by new coordinates x dash y dash. Okay, and that would actually give you just okay, that is just rotating the vectors over here. Okay, sorry about that because I've forgotten what I'm supposed to say. Right, but remember that the original problem is actually this one. Okay, so we have a transformation from this small r to this big R over here using the matrix M. Well, we can relate to this equation with this equation by just multiplying, no, or here you can, instead of your small r dash and small r here, I can rewrite this in terms of capital R dash times equals to C times capital R, and then your capital R is related to the small r in that way, and then finally you can use the, which equation was that, this r dash over here, so r dash equals to CR, so R would be C inverse R dash. So in other words, now what we have is to relate the new coordinate system of the rotated vector to the new coordinate system of that original vector, but no, in the new coordinates. Okay, so in other words, what we have is looking at this kind of transformation. So initially we had this original coordinates x and y, but under the transformation we do rotations, okay, in a way that when you do the rotations, then the things, the vectors get sort of pointing in the direction of your x dash and y dash. So that was the thing that that was the thing that was supposed to tell you over here. So this, remember, is now your D. Okay, so essentially your axis that was here before was rotated over here. So this gives you one of the axes for the new coordinates r dash, and then if this is rotated that way, then this is also going to be rotated. So this gives you the new coordinates y dash, and that corresponds to your no, the new capital R dash. Okay, and essentially this transformation between small r dash to capital R dash just simply says that, you know, that your vector is along the direction of the eigenvectors. Okay, so I'm not explaining this particularly well, but I hope you can see some form of relationship between diagonalization with a rotation in such a way that the rotation gives you a way of turning a matrix. Okay, the matrix M initially, does something like this better. So M sort of rotates your small r to capital R, and then your D is now coming from what is it, CMC minus 1 rotates R dash to capital R dash. Okay, so that essentially the idea of diagonalization there. But there is one thing before before we think that this is going to be general enough. The matrix that we started off with in this particular case, we look at the matrix M, is a symmetric matrix. Okay, so there lies certain condition for you to look at in order for you to do diagonalization, that your matrix M will have to be a symmetric matrix. And then the other thing that one can actually check, the eigenvectors, okay, the one x1 and y1 that we have actually find the equations for those, okay, the lines, okay, they are orthogonal to each other. Okay, so you can check, for example, here's the eigenvectors for x1, y1, and this is x2, y2. Okay, so you take the dot product, or take the essentially, well, it's the dot product. Okay, it's just one of them turned into a row vector with a multiplying column vector. Okay, and that gives you a 0. Okay, so we have to take note of that conditions before you are able to do diagonalization. So some points to consider for diagonalization. So I hope okay, this is not so smooth as I wanted, but essentially the idea is to have some geometric understanding of this process. Okay. Otherwise, if one gets confused with these ideas, one treat this as just like an algebraic equation, and then you just solve for eigenvectors and eigenvalues. But then in order for you to understand the diagonalization, okay, why the diagonalization gives you this particular matrix in the first place, okay, this matrix C, for example, then you need to understand a little bit more on the geometry side. Okay, right. What else? Perhaps, okay, here's another a bit more elaborate example, which instead of 2 by 2 matrix, we can now extend it to a more general matrix, which I think I will try to take a break now instead of continuing. Is that okay? Okay, so let's take a 5 minutes break. Okay, I hope everyone is back. Or not? Okay, so let's just continue with this second example. So here's a 3 by 3 matrix. So again, remember one of the things that we want to check in order for this to be diagonalizable is that the matrix is symmetric. So if we look at the off-diagonal elements over here, element 1, 2 is equals to element 2, 1, element 1, 3 is equals to element 3, 1, and what's the other one element? Getting confused. Here is the element 2, 3, and that should be equal to the element 3, 2. So in other words, this is actually a symmetric matrix. So one can actually diagonalize this matrix. So it's diagonalizable. So how to find the diagonalization process? Then what one needs is to write down the characteristic equation again. So what is the characteristic equation? Is this matrix. You take the determinant, and then set this to be equal to 0. Okay, so this is essentially this equation here. But of course, unlike the case of the 2x2 case, we need to do expansion of this. So over here, I'm taking the first row, I think. Well, actually, it doesn't matter. It goes that way as well. Okay, so I'm taking the first row, and then the determinant of that, and then second element of the first row for which multiplies with the -1 over here. Okay, and that gives you this, that. Okay, and then the last one is going to be that. So I would have this the 2x2 determinant from there. Okay, so expand that again, and then try to find the equation here again, because it's a 3x3 matrix. One gets instead of quadratic, what do you call this? Well, it's a cubic equation. Cubic equation in lambda, which is slightly harder to solve. With quadratic equation, you have the quadratic formula, but here you pretty much have to guess a little bit. So the usual way I do things is to look at this particular number. So this is 54. So what are the factors of 54? So it will be 9 times 6 over here. Then I will get this particular factorization. Okay. So and over here, essentially there are two eigenvalues are the same. So in other words, lambda equals to -3 is what we call the degenerate eigenvalue. Lambda equals to 6 is non-degenerate because it only occurs once. So the best thing is to start with the non-degenerate case, because the degenerate case tends to give you more problems than the non-degenerate one. Okay, so one starts with lambda 1 to be equals to 6. So again, these are the eigenvalue equations over here. Okay, and one can actually try to solve what they are. So you get 3 sets of equation with some of them could be actually written as a parameter of another. So one could actually get this particular solution x1, y1, z1 over here by solving this equation. Usually you need to fix one variable. Okay? Fix one variable as a parameter. Okay, and then solve that, and if possible, normalize this x1, y1, z1, and it so happens to give you this particular eigenvector. Okay, so this is the first eigenvector corresponding to lambda 1 equals to 6. Okay, so if you try to do for the case of the degenerate eigenvalues, then one of the problems that you probably will find is to see that the 3 sets of equations over here are proportional to each other. So in other words, one needs a little bit of creativity to see how to separate out remember that each eigenvalue, including the degenerate one, okay, would supposedly give you one eigenvector, okay. But remember what one can actually do. Okay, since these equations are proportional to each other, we don't have enough equation to actually solve even in a parametric form, or in the fixing the one of the variables, for example, because they are all probably the same equations, okay, because proportional, okay. So one has to probably just pick and choose what you call a set of values that would actually solve this equation. So here, let's take, for example, x equals to 1, or x equals to minus 1 in this case, x equals to minus 1, and then y equals 0, and z equals to 2, and substitute that, and that will definitely give you 0. So we can choose that to be one of the eigenvector if you want, okay. And then another eigenvector would be sort of another set of points that solve the same equation. So another set of points that solve the equation here would just take x equals to 1, y equals to 1, and z equals 0. Okay, that gives you that. But now your two set of vectors that you have here, the r tilde 2 and r tilde 3, they are not orthogonal. When you take the dot product, for example, this will not give you a 0. So remember, one of the properties that we observed in the first example just now, okay, was that the eigenvectors should be orthogonal to each other. So what does one do is, okay, one of the things that we have already learned is orthogonalization from Gram-Schmidt procedure. I'm not sure which lecture was that, but what one does is to take one of the vectors. For example, here we take to be R3, find the norm, and then normalize it. So in this case, we take the simplest one. R3 is that will be simpler. And then if you normalize this, you get 1 on square root 2 in front. So that's what we have over here. Okay, so this is now normalized. And to ensure orthogonality with the other one, you remove this what we call component away from r tilde 2. So what we do, take r tilde 2, dot product with r3, which is now that, okay. So that gives you how much of this part gives you how much of this the r tilde 2 in the direction of r3. Okay, so and then of course you remove that direction r3. Okay, so once you do that, you get this algebraic equation to calculate, and that gives you this vector r2. Oh, not yet. R2 is, you need to normalize that. So R2, so normalize this vector, okay, and then you get R2 here. Okay, so now you can check, okay, your R2 dot R3 should be equal to 0. Please check for that. Okay, so now one can also check with the R1 before. Okay, so R1 dot R2 is also 0, R1 dot R3 is also 0. Okay, So we have now the orthogonal eigenvectors. Now you can actually use that to form the C matrix that we had earlier. So what do you do? The C matrix should be something like this. It's just arranging R1, R2, R3 as columns, and that will give you the diagonalization matrix. Okay, so I will not do that and leave that to your as an exercise. Okay. Try to complete this. Okay. Okay. So the next thing that we want to do for today, before we still have a bit of time, next thing that we want to do is essentially try to apply this to even complex matrices. The one that we have done, the two examples before, is actually real matrices. So now we claim that we can also do this diagonalization of complex matrices, but again, one needs some condition. In the case of the real matrix, we need symmetric matrices before you can diagonalize that. So the symmetric matrices are diagonalized by using orthogonal similarity transformation. Okay, and the orthogonal is transformation is essentially a rotation there. Why you need that is because you have this property there. Okay. And for when you generalize for the case of complex matrices, we need something similar. We need some analog of this equation and some analog of this equation. So for complex matrices, you don't only have transpose, you also have complex conjugate. Okay, so combination of the complex conjugate and the transpose is essentially your adjoint operation. Okay, and then the equation that you need over here is supposed to be something of this type of equation. Okay, so for complex matrices, just to summarize over here, for complex matrices, the condition for diagonalization is that you have instead of this one gives you the symmetric matrix. Instead of that, we should have this one, which is essentially tells us, okay, you remember we have discussed about the special classes of matrices. This is what we call Hermitian matrix. And this is important because in quantum mechanics, one has those types of equations. Okay? Sorry, matrices. So what about this condition now? Okay, your transpose is now supposed to be a combination of complex conjugate and the transpose, and that gives you the adjoint here. And this essentially also you have learned about what kind of matrices are these. These are called unitary matrices. So like I think I've mentioned before, your unitary matrix is like a rotation matrix, but for complex vector spaces. Okay, so these are sort of the version of your, okay, for this one is the version of your symmetric matrix. For this one is the version for your rotation matrix. Okay, and if you have done, I think you probably have not done it. If you're going to do quantum mechanics, your unitary matrix are in fact are just telling you how to transform one basis to another basis. Just a rotation matrix, it transforms from one set of coordinate system, one set of bases, to another coordinate system, which is another set of bases. Okay, it's the same kind of thing. Okay, one lives in a real vector space, the other is living in the complex vector space. So let's try to do the theory of this again, and hopefully we'll finish up with this part of the what you call section of this lecture notes. So again, we'll start off with some matrix here. So remember, this now has to be Hermitian. So you look at this, for example, this 1, 2 element of this matrix has to be equals to this 2, 1 element of this matrix, but with a complex conjugate. And this one will have to be complex conjugate of that. And final one is that, has to be a complex conjugate of that. Now what about the diagonal elements? The diagonal elements has to be real. Okay. So now we consider the eigenvalue equation of this, just like in the real case. Okay. But what's now possible to prove is the following. Consider the left hand side of this equation, which is that. Okay. Now I can apply the transpose, or the adjoint, sorry, to that part of the equation. So that gives me HR dagger. So this is like this matrix here. Okay, so you have this say 3 by 3 Hermitian matrix here, and then this vector in three-dimensional complex vector space. Okay, it's a bit noisy with the air conditioning on, so let me see if I can switch it off. No, I think it's the other room. Sorry about that. So you have to, can you still hear my voice? Okay, so it's a bit noisy with the air conditioning. So what we're going to do is to take the adjoint of this whole equation, in fact. So here's the left hand side. So I have HR adjoint, which gives you R adjoint, H adjoint. What happens, this is like going from 3 by 3 matrix times 3 by 1 3 matrix times 3 by 2 matrix. Okay, so this is the process of the adjoint there. Okay, and then the left hand, sorry, the right hand side, you do the same. Okay, find the adjoint, but the adjoint over here is pretty simple because this is a scalar, but the scalar now can be complex. Okay, so in other words, this can be complex conjugated here, and then R dagger is your adjoint of your R over here. So put them together in the equation. So essentially we are doing the adjoint of this equation here, then you have this equation. Okay, so let me just write that down, and then okay, maybe I'll do this here. So what happens over here now, I can do the following. For this one, I multiply by R on the right. For this one, I multiply by R dagger on the left. Okay, so when that happens, I will have the following. I have this equation, and the other one will give you this equation. This from the top one. Okay, so R dagger HR lambda R dagger R, so that's that. And this one is from this second equation, R dagger HR, okay, R on the right, and then lambda star here, R dagger R. Okay, so you have two sets of equations from the two equations over here. Okay, but now if you look at this, okay, your left hand side is the same. So if I take the difference between these two, okay, the difference between these two, then this minus this will give you 0 here, but this minus this will give you this, because lambda here is different here. So here is lambda, here is lambda conjugate, despite this is actually the same. Okay, R dagger R, R dagger R, but lambda and lambda star can be different. Okay, so now taking the difference between the two equations over here will require us to have this equation to be true. Okay, so there are two ways of making this equation to be equal to 0. Either you have this equal to 0 or you have this equal to 0. Okay, so let's consider this to be equal to 0. That means lambda star has to be equal to lambda, or in other words, lambda has to be real. So the eigenvalues are real. Okay, and the eigenvalues are real because it belongs to the Hermitian matrix. Okay, and then let's consider the case where you have two different eigenvalues and two different eigenvectors here. Okay, this one. Okay. Then you'll be able to show that if one has that, okay, what happens over here, I need to do the multiplication again. So one is this equation. Okay, for this equation over here, I will multiply with, say, R2 dagger here. Just check the one below. Oh, I need to do the other way around, sorry. I need to do this equation. So I multiply this by R2 here, and same thing over here. I will multiply this with R1 dagger. This one multiplied by R1 dagger. Okay, and then again take the difference between the two. There you see that, okay, one has this kind of equation over here. Let me just write it out first. You have R1 dagger HR2, okay, from there, and minus this, minus R1 dagger HR2, so they are the same, so that will have to be equal to 0. And then you have the left hand side here, sorry, the right hand side here, that will be lambda 1 R1 dagger R2, sorry about that. So this will be lambda 1 R1 dagger R2 minus lambda 2 R1 dagger R2. So simplifying the equation now, then you see that okay, since we want it to be a different eigenvalue equation for R1 and R2, so lambda 1 and lambda 2 is not the same. Okay, so then lambda 1 and lambda 2 is not the same. Then the only way that this can be 0 is that these two vectors are orthogonal to each other. Okay, so in other words, the gist of what we have done so far is to show that the eigenvalue of Hermitian matrix are real, and then the eigenvectors corresponding to different eigenvalues are orthogonal. Okay, so again, just following through what we have done in the case of the real matrices, one could now diagonalize the Hermitian matrix, okay, in very much the same way like before. Previously it was C minus 1 MC equals to D. Now you have, instead of C, you arrange again your eigenvectors. Okay, your eigenvectors are still forming the matrices C here. So instead of C, just to differentiate with the real case, we write it as U. Okay, and then your U inverse here, since this is unitary, then U inverse is just your U dagger. Okay, so again the theory is very much the same, apart from the complication that you have complex matrix elements. Okay, then this we have done before. Okay, now let's look at an example. Here's a Hermitian matrix. How do I know it's Hermitian matrix? First thing, the easiest thing to check is the diagonal elements. So the diagonal elements of Hermitian matrix has to be real. So this is real, this is real. For the off-diagonal one, well, this element has to be the complex conjugate of this element, which is, in this case, it's true. Okay, so now one can actually try to find the eigenvalues. Again, the eigenvalues is coming from solving h minus lambda I, taking the determinant equals to 0. Okay, very much the same way for your real matrix. So you do that, okay, and then you'll find that, okay, you have this quadratic equation to solve, okay, and that gives you your eigenvalues. Okay, so there are two different eigenvalues. So one is lambda equals to minus 3. So we have to solve for the eigenvectors. We write the eigenvectors as labeled by the eigenvalues themselves, x minus 3, y minus 3, and then you can actually find the two equations over here. Okay, and one can use one of them to be the parameterized, the independent variable, and one is the dependent variable. But the best way is just to look at the conditions of the equation themselves. Okay, so here one can choose x minus 3 equals to 2. Okay, and then y minus 3 equals to minus 3 minus I. Okay, which coming from that. Okay, so and then normalize it. So you need the norm over here. Remember, the norm now involves also the what you call the imaginary component. So you have this 3 squared plus 1 squared coming from there, and then you normalize that, and that is essentially your eigenvector for lambda equals to minus 3. I'm not going to the details because I think you can look at the calculations later on. Similarly, for lambda equals to 4, again you get the set of two equations over here. Again, choose the one which is convenient for us here, choosing y4 equals to 2, x4 equals to 3 minus I. Again, it's related to the entries over here. Okay, so and then normalize it again. And after all the calculations, you have to make sure that your eigenvectors, one of the properties that we know just now, your eigenvectors has to be orthogonal. So one can check, for example, and you have to remember that they are now complex. So you need, when you do the adjoint, you have to take the complex conjugate. Okay, so in this case, you have that, and then multiply with that, and then you can check that this is essentially your orthogonality condition. What about the matrix U? Well, it just comes from the eigenvectors. So the eigenvectors, remember this one and this one, no, the other one, sorry. This, where is it? X minus 3, yeah, this one, okay? And put them into a column form, and basically that gives you the matrix U, and then you can form the adjoint just to check, form the adjoint, and then check that U dagger is equal to I, okay? And you can confirm that. And then finally, what we need is this diagonalization part. Okay, so when you multiply U dagger each U, then you find that you get a diagonal matrix. So that is very much what I wanted to say for today. For the next lecture, which I have not quite finished the notes as yet, for the next lecture, we will see where does this can be applied to this idea of diagonalization. One of the properties is, for example, we'll look at a few physical problems. One is a problem of ellipse, for example. The normal ellipse that you have in this particular form, okay, you normally have this kind of thing, but this is not the most general. The most general ellipse will have in any direction. Okay, so here, if one can think of this to be the axis being rotated here, then one could get back to the standard form, which is the one I call the diagonal form. But otherwise, over here you might have things like this. There will be some things like that. Sorry. Oops. The equation of the ellipse becomes a bit obscured in the sense that there is a mixed term over here, and this will be equal to something. Okay. And then the other problem is the problem of couple spring, so we can try to do that as well, and probably other things as well. Okay, so that will be the next part, the next lecture or so that we go through some examples of these applications of diagonalization. So I think I want to stop there for today. It's getting very noisy and I'm a bit tired. So let me stop now. Okay, oops, what did I do? I want to take the attendance. And then the other thing that I wanted to do is, so the attendance have been taken. The other thing that I wanted to do is, can you see the whiteboard here? I want you to please discuss the following. One is the replacement lecture that we have missed. This, come on, okay, at least 1.5 hours. And then a second one is your SCL, okay, module. Well, I'll give you some papers to review. Hopefully I can do this by tomorrow. And then this SCL module, I think I asked you to do the assignment in pairs, right? Last time? Okay, so this one, we'll do it in groups of 4. So these papers, I will try to find some papers which related to your topics of the course. The other one is, please check your results. Check your test 1 results, and I need to, I need, for those who are having less than 8 marks, probably you need to come and talk to me. So we can arrange for a particular time, just a short discussion about what you have done, and then probably you need to learn from your mistakes. Okay. So please discuss this, and then I think that's it for today. So are there any questions so far? I've not uploaded the recent lectures because I just updated some of the points there. So I'll probably try to upload it sometime today or tomorrow. So that's it for today. Any questions or queries? If no, then we'll stop now. So thank you, everyone. Okay, bye, everyone.